So in this video, I am to show that a subset of a subset of W of a vector space V is a subspace if and only if. So I'm gonna talk about this part of the sentence in a second. Is a subspace if and only if span of W is equal to W. So at first, when you see a question like this, hopefully it's not in a test because this is a pretty difficult question. But if you do, the first thing is you see a proof question and you don't know what to do. You need to sort of break it into steps. So no one ever gets a proof the first time they do it. Only geniuses do, and I'm certainly not a genius. But I can give you tips and steps to sort of get the proof going. Okay, so don't expect to get this kind of proof the first time you do. If you do actually get the proof the first time you do, then congratulations, you're much smarter than most people. If you don't, though, that's very normal. I couldn't get it for maybe a day or so, and finally I had to go to my professor. So what you do in these kinds of situations is you need to break the proof down. You need to basically break your sentence down. So show that a subset of W of a vector space V. So basically we're given that W is a subset of V. We're given that W is a subset of V. So that we can't argue with it. That's given in the question. So now we have that W is a subspace. So now we are to prove. So we are to prove that W is a subspace of V. Remember, this is the shorthand for V. If and only if. So now I'm going to write the sort of the shorthand notation for an if and only if. It's a two-sided arrow. We usually write it like this. So W is a subspace of V if and only if span of W is equal to W. So let me give you a quick proof concept on an if and only if. So proof concept for if and only if. Proof concept for if and only if. We also write if and only if in shorthand like this. So it's either like that or like this. So in an if and only if, it's sort of, if you want to think of it like in basic terms, it's like you have A if and only if B. So this proof has two steps. So there's two steps to this proof. Two steps to this proof. The first step, or the first direction, usually we call it the first direction. And the reason why we call it the first direction is because the first direction is like this. So that's our first direction. We're starting with A, and we want to prove B. So we go like this. So we assume A, want to prove B. Want to prove B. Similarly, for the other direction, for this direction, right here, we have, well, usually what most mathematicians do is they write the other direction like this. So we assume B, and we want to prove A. So this is usually, well, no, this is always how you're supposed to set up. So this is the setup to an if and only if. So this is the setup to an if and only if. Okay, so now let's try to give it a. Let's try to give it a go. So you don't really need to start with this direction first or that direction second. You can interchange them. It doesn't really matter. Sometimes it's easier to start with the other direction because it's easier to prove, and then you go on to the next one because it's harder. Some people like to do that. In this case, what I'll do, I'll start with, you know what, I think I'm going to start with the normal direction. I'll do this direction first. So usually you start the proof by writing a single-headed arrow like that. And so what I'm doing is I'm assuming A, right? So in our case, A is that W is a subspace of V. So I'm going to assume that W is a subspace of V. So this is my assumption. Now what I'm supposed to prove, I'm supposed to prove that span of W is equal to W. So another proof concept is when you're trying to prove the equality of two sets. So span W, as we know, is the set of all linear combinations of vectors in W, right? So that's one set. And then we have the set W, which just contains all the elements in W. That's just a definition of a set. So we want to show that two sets are equal. So this is another proof concept for showing that two sets are equal. Okay, so this is an aside, but it's a very important aside to actually prove this statement. So let's say we have A and B. A and B are sets, right? So we have A and B as sets, and we want to show that A is equal to B. Then what we have to do, and this is kind of an if and only if, in the sense that there's sort of two directions or two steps to it. So there's two steps to it, in that the first step is to show that A is a subset of B. Okay. So now you're going to ask, well, how do you show that A is a subset of B? Well, this is kind of another proof concept. So this is another proof concept. I know there's a proof concept and a proof concept, but you'll see why I'm sort of focusing on these proof concepts, because these come back very often in linear algebra proofs. So proof concept, showing that A is a subset of B. Okay, so how do you show that A is a subset of B? So in other words, if this is my B, and this is my A, right? I want to show, well, you can see visually that A is a subset of B, but I want to prove that A is a subset of B, because this is what A being a subset of B means visually. But I want to show this. With with an actual formal proof. So the way to go with this is that you take an arbitrary element or vector or whatever. So element or vector. Take an arbitrary element or vector in A. So that's an N in A. And you show that this same element is in B. Okay, so what do I mean by that? That might sound a bit confusing at first, but what do I actually mean by that? Well, let's say you say, so you'll start by saying, so you say take A belong to A, right? So small a belong to big A. So visually what that means is I'm taking an element A, that belongs to A. And I want to show that A also belongs to B. So I want to show that A also belongs to B. But why am I doing this? Because if I show that I take an arbitrary element in A and necessarily it's in B, then that means that any element I take in A, so why am I doing this? That means that any element in A will be in B. Because if I show this, so I need to show this, I need to actually prove that this is true. But if I do show that A is in B, if it's already in A, then that means that any element in A is also in B. So that's how the logic goes. You want to start by saying A belongs to the set A, and somehow, so you'll see how in the proof, somehow you want to get to saying that small a also belongs to its superset. So in this case, B is a superset of A, and A is a subset of B. So you want to say that A belongs to its superset. So that small a belongs to B. So that's basically what you're trying to show. So that's the first part. So remember we're in another proof concept. We're trying to show that A is equal to B. So step one is showing that A is a subset of B. And you do that by saying you take any element A in A and show that A also will. That does not look like also. A also belongs to B. Why? Because if you take an arbitrary element in A and you see that it's in B, that means you can say that any element in A is also in B. Now, you might have guessed what the second part of the proof is. The second part of the proof is pretty much the same. It's just you're trying to show that B is a subset of A. And again, you do that by saying you take an element B in B and you show that B belongs to A. Okay, now why am I doing this? Why am I doing B belongs is a subset of A and A is a subset of B to show that A equals B? Well, think about it this way. B is a subset of A. That means that anything in B is going to be in A. Okay, but this alone doesn't tell you that A is equal to B. There could be stuff in A that's not necessarily in B. The same thing here. There could be stuff in B that's not necessarily in A, but you know that everything in A is also in B. So this, when you have an equality of sets basically means that the two sets have the same exact content. So they have the same exact content. So you show that they have the same exact content by showing that the first set is a subset of the second set. In other words, that everything in the first set is in the second set, and vice versa, that everything in the second set is in the first set. So by showing these two things, you have no other choice but to conclude that A and B, the first and the second set, have the same content. So remember that this is all about content of sets. Okay? So I know this is a very, very long parallel. You could have skipped this if you had already seen this. Also, I'm sorry I'm rambling on, but I just want to make sure that you guys you get this before I start the actual proof, because the actual proof is just using these concepts. Okay? So remember what I was trying to prove. That span W is equal to W. Okay? So after all of this, I'm going to start. Remember how to show the equality of two sets. I need to show that the first one is a subset of the second one, and the second one is a subset of the first one. So how am I going to show that? Well, first I'm going to show that span of W. So span of W is a subset of W. So what I'm going to do, remember how to show that something is a subset of another thing. You start with saying that if something belongs to span of W, then it must also belong to W. So let's say let X belong to span of W, right? So you have to start somewhere. That's where you need to start in a subset proof. So let X belong to span W. But what does this mean? What does it mean to belong to the span? What does this mean? Well, if X belongs to the span of W, that means that X can be represented as a linear combination of the vectors in W. So that means that X can be represented as a linear combination of W. So in other words, we can write X as A1 W1 plus A2 W2 plus dot 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 plus AN WN. Okay, where W1, W2, W3, W whatever, WN, these all belong to the set W, and where A1, let's change color, where A1, A2, A3, whatever, AN, where these all belong to the set of real numbers. In other words, I'm just stating what this means. So this directly, if I say that X belongs to the span of W, that directly means that X belongs to this thing. X belongs to, well, no, not sorry, belongs. X is equal to the linear combination of the vectors in W, which is this, assuming that there are a certain amount of vectors in W. So, okay, I have this. Now remember what my goal is. My goal is to show that X belongs to big W, to the set W, right? Well, how do I show this? Well, let's think about it for a second. So what do we know about W from our assumption? From our assumption, which is where here, we assume that W is a subspace. W is a subspace. So what do we know about subspaces? Well, what do we know about subspaces? W is a subspace, right? So that means that W is closed under scalar multiplication, meaning that if X belongs to W, then Cx also belongs to W, right? That's just by definition of subspace. And W is closed under addition. Meaning if I have X and Y belonging to W, then X plus Y belongs to W, right? So that's just by definition of a subspace, okay? Well, what really is X then? Well, X is a scalar times an element in W plus a scalar times an element in W plus a scalar times an element in W, and so on until a scalar times an element in W. Basically what's happening is I'm taking the scalar multiplication of a vector in W. So let's say I'm taking So let's say I'm taking W, I'll say Wi, where I is 1, 2, it's anything between 1 and n, right? So that's fair. This is just a certain notation to say Wi, where I is between 1 and n, because here we've listed the vectors in W as W1, W2, W3, Wn. Okay, so we have a vector Wi, and we're multiplying it by a scalar ai. Wi. So we know that Wi belongs to W, and now we have Wi, where again, so we know that I is between 1 and n, and Ai belongs to the real numbers. So we know because W is a subspace that this belongs to W, because W is closed under scalar multiplication. Right? So if I multiply any scalar by an element in W, so in this case Wi, it will belong to the set W. That's just the definition of a subspace. Now, if we take two of these, two AIs plus AI WIs, so if we take two scalar multiplications of vectors in, well, two distinct, right? So we're dealing with two different vectors of two vectors in W. So let's say we have we have AI WI and let's say BJ WJ, where I is between 1 and n, and j is between 1 and n, and I is not equal to j, because these two are distinct, right? We want them to be distinct. Okay, so if we take AI WI and BJ WJ, we know that these two will belong to W. And if I add them, AI WI plus BJ WJ, these two will belong to W, because W is closed under addition. And I can repeat this exercise. I can basically repeat this logic for all of x. I can repeat this for all of x. Now, some of you who may have taken a proofing class would say, well, this is clearly a proof by induction. I'm not going to go into a proof by induction because that's not really the goal of linear algebra courses usually. You certainly can prove it by induction, but I think just showing the logic here is the most important step. So I'm taking a scalar multiplo of any element in W, and I'm adding it to a second scalar multiple of a different vector in W, and I'm doing that forever and ever. So let's say I'm adding A1W1 to A2W2, then adding that to A3W3, then adding that to A4W4. So you get the picture until ANWN. So all of those scalar multiplications added to other vectors will belong to W, because W is a subspace. So that's just a property of a subspace. So I know I'm rambling on, but this is a really important and fundamental concept of span and of subspace. So because of this, so basically because of this, so basically this being that W is closed under addition and scalar multiplication, we can say that X belongs to W, right? So X belongs to W, meaning that span of W span of W is a subset of W. Okay. Now, the second part of the proof is, because remember this has, I know this is very long, but I'm trying to show that span of W is equal to span of W. That span of W is equal to W. So the first thing I need to do is to show that span of W is contained, or is not contained, is a subset of W. The second part is showing that W is a subset of span of W. Now, this part is a bit easier, because if I just say, so if I let X belong to W, okay, then I can say that X is equal to 1 times X, right? So 1 belongs to R, and X by this assumption belongs to W. So that means that X can be expressed X can be expressed as a linear combination of vectors, well, in this case, of the vector X in W, right? Because by definition, like clearly, I can write X is equal to 1 scalar multiplying X. So X can be expressed as a linear combination of the vector. In this case, it's just one vector X, but it's still in W, so that counts. X counts as X is equal to 1 times X, counts as a linear combination. So since X can be expressed as a linear combination of a vector in W, then by definition of span, so by definition of span of W, X belongs to span of W. So I should do the second part of this proof in this video, but I think that's a bit too long. So I'll end it here, and then we'll do the second part and another one. But this was a very important part in a very important video, and explain to you most of the proof concepts that you'll see in linear algebra. So basically, we have the if and only if. We have the equality of sets. So we had the if and only if here, the equality of sets here, showing that for equality of sets, you need to show that A is a subset of B, B is a subset of A, and finally showing how to prove that something is a subset of something else. So with that, I hope that was helpful, and I'll see you next time.